We will talk about the homogeneous equations. Now, homo means same. Homo means same. So I can say that those equations, an equation is said to be homogeneous. Homogeneous if all of its terms have if all of its terms have same SI base units. So it means if equation is said to be homogeneous, it must have the same SI base units. For example, if A plus B is equal to C plus D, if this is a homogeneous equation, then unit of A, unit of B, unit of C, unit of D must have the same SI base unit. Here the common sense tells us, for example, if you have to add 5 kg plus 3 kg, it is 8 kg. But if you have to add 5 kg plus 3 meter, you cannot say it is 8 kg because you cannot add definitely 5 kg and 3 meters. So if an equation is there, addition or subtraction, the terms can be added or subtracted if it has the same units. Are only two terms, one on the left side, one on the other side, it must have the same SI base units. Then it's a homogeneous equation. Now, homogeneity does not guarantee an equation will be correct. If an equation is homogeneous, if an equation is given to you, and first you have to say it, whether it will be homogeneous or not, or correct, or what the table says. Table says if you are given an equation, first you have to see whether it is homogeneous, whether it is homogeneous or it is non-homogeneous. If it is non-homogeneous, then it must be an incorrect equation. This is definitely incorrect equation. There is no question. And if it is a homogeneous equation, it may be correct, it may be also incorrect. So suppose then we can say homogeneity is actually the first check which tells us whether an equation will be correct or incorrect. Suppose you are given 100 equations and then you will first test on the homogeneity. If the equation is 5 equations are homogeneous and 95 are non-homogeneous, then you will straight away reject those 95 equations and you will take only 5 equations for your experimental purpose, and you will select only one equation. So when equations are incorrect, why the equation is incorrect? There can be some missing terms. Due to some missing terms, it can be an incorrect equation. For example, we know that V is equal to U plus AT is a correct equation. V is equal to U plus AT is a correct equation. But I suppose if I delete U and write just equation V is equal to AT. Now this is the unit meter per second. This is also meter per second square into second. This is a meter per second also. So equation is definitely homogeneous, but it's incorrect due to missing term. Okay, then there can be some additional terms also. Now they can suppose S is equal to ut plus half at square is the correct equation. If I add a term Vt, now definitely this is the unit meter, this also meter, this also meter, this also meter. You can verify. Meter per second meter, half at square, a meter per second square into second square meter, meter per second into second will also be meter. So this is this definitely a homogeneous equation but incorrect. Then there must be some wrong coefficients. Now if there are wrong coefficients, suppose if the equation is V is equal to U plus AT is a correct equation, and suppose if I write 3V, 5U plus 7AT, now this will be definitely an incorrect equation. So when an equation is given, whether it can be homogeneous or non-homogeneous, non-homogeneous equation is definitely incorrect, and if a homogeneous equation, it can be correct or incorrect. If it is incorrect, there may be 3 things. Due to 3 things, it will be incorrect: missing terms, there can be any one missing term or 2 missing terms, then there can be some additional terms, and there can be some wrong terms. Now examiners usually give some equations and they ask whether it's homogeneous or not. The famous equation is, they say P is equal to rho GH, you have to show that P is equal to rho GH is a homogeneous equation, or he may say is a homogeneous equation, you have to show is a homogeneous equation, or sometimes he may say is a, or he may say is a dimensional, is dimensionally a correct equation. He may say this also. That a correct equation. When he says dimensionally correct equation, it means it is homogeneous with respect to units. Also, our dimensions in physics is something different, which is not in A levels course. But when he says, suppose he says prove that it's dimensionally correct equation, then we have to prove it by the unit analysis. Now I will take the units of P. Units of P. P is pressure, it's Pascal. Pascal can be Newton per meter square. Newton is kilogram meter per second square. Into meter m power minus 2, so this will be kg m power minus 1 s power minus 2. So units of P in base SI units is kg m power minus 1 s power minus 2. These are the multiplying signs. Then I will say what are the units of rho GH. This rho is the density. Rho, please care must be taken between the rho and P. This is P and this the rho density. Density is kg m power minus 3, g is m s power minus 2, h is length or height or depth, it's meter, so it will be kg m power 1 and 1 2 minus this minus 1 s power minus 2. These are the same units, so I will say the equation P is equal to rho g, which is the dimensionally correct equation, or it's the homogeneous equation. Similarly, suppose examiner gives this equation. He says prove that mgh upon t plus mv square upon t is equal to force into velocity. Okay. Now, all right, whether it's a correct equation or incorrect, I'm not concerned with that. Actually, this is an incorrect equation because it's the potential upon time, that's the power with respect to potential energy, but it's the kinetic energy too is missing, so it's definitely an incorrect equation, but I'm not bothered with that, whether it's a correct equation or incorrect. I have to see here, I have to show it here, this is a homogeneous equation. So if this is homogeneous, I will say units of mgh upon t. M is kilogram, g is meter per second square, h is meters, height upon t second. This becomes kilogram meter square s power minus 2 s power minus 1. So it's kilogram meter square s power minus 3. Similarly, it's units of mv square upon t. M is kg, and of course ms power minus 1 whole square upon time in second. This will be kg meter square s power minus 2 s power minus 1. So again this is kg m square s power minus 3, same units. Now units of Fv, force into velocity. Force is Newton, velocity is meter per second. Newton is kg meter per second square into meter into s power minus 1. Again this becomes kg m square s power minus 3. So we can prove this way. Sometimes examiners give another additional term. Suppose they can add here. Suppose they say what is the unit of the k in this equation. Now the equation is mg upon t. We saw k. Actually, this is homogeneous equation of this one. Now k must have the unit of what? Units of k must be also this one. Units of k must be kg m square s power minus 3. Or since you know, if you have the watt is joule per second, joule is Newton into meter per second, and Newton is kg meter per second square into meter s power minus 1. If you resolve this, kg m square s power minus 3. So you can assign this k as a watt also, but you can have the base SI unit, this one also. So this way we can prove, we can show whether the equation is homogeneous or not. When it's all terms have the same SI base units. Sometimes the examiners say some quantity and ask for to find the unit of that one. For example, if you are given F is equal to suppose G m1 m2 upon r square, a famous Newton's gravitational law, which is in A2 level, second year of A2, and he says for what are the units of G? You have to find units of G. Now I'll first make the subject vector G. G will be fr square upon m1 m2. So I can say units of G will be Newton meter square upon kg into kg. I can say Newton meter square kg power minus 2. I can leave it here. So unit of G can be this one. But if I want to find SI base units, then Newton is kg meter per second square into meter square kg power minus 2. So this is kg power minus 1 m power 3 s power minus 2. These are the units of g. For example, once in the physics practical AS level, an equation was given. The examiners were asked to verify what actually to drive the units of a upon b, b upon a, and what are the units of a and b. The equation was this one: t square is equal to minus bx plus a, where t is time period and x is length. They say what are the units of b and a. So I will write first units of t square and secant square. So I clearly can say units of bx will also be secant square. So units of b will be secant square upon units of x. So it will be secant square upon meter, or it will be secant square n power minus 1, units of b. And units of a are just secant square. It's t square secant square. So suppose he says what are the units of a upon b, then I will say a upon b secant square upon secant square m power minus 1. This is s power 2 minus 2 and m power 1, s power 0 into m, s power 0, anything power 0 is 1 into meter, so it's meter. I can just cancel here also, and I can say it's m also. I can proceed in that way. So these are the things. In that way we can find the units of b and a by the homogeneity